Hello everyone, my name is Lukas Macedo and I'll be presenting our work titled Analysis and Prediction of Lithium-Ion Battery Degradation in Equatorial Environments Using a Hybrid Approach, developed together with Raphael Nunes, Luiz Eduardo de Silva, Iury Bessa, and Renan Landau de Medeiros. Now, to put this work in a current context, it has been observed a global concern over climate change in recent decades. According to the World Meteorological Organization, the 2015 to 2024 temperature readings have been the warmest ever recorded, and 2024 itself was the hottest on record. This growing trend has motivated countries worldwide to commit to the net zero initiative in reducing carbon emissions and transitioning toward cleaner energy sources such as solar, wind, and geothermal. The demand for energy storage systems has skyrocketed. In accordance to the review published by the IEA, the International Energy Agency, the global battery yearly demand rose from around 75 gigawatt hours in 2017 to 700 gigawatt hours in 2023, showing how critical batteries have become in modern energy infrastructure and electric mobility. However, this rapid growth also brings challenges. Researchers are now focusing on understanding how batteries degrade over time, how to improve their efficiency, safety, and longevity. And one of the bigger factors in battery degradation is the operating temperature. Depending on what ecosystem a battery is operating, different negative effects can be expected, such as faster capacity loss on warmer climates or reduced nominal voltage in colder ones. Most studies so far have been conducted in temperate or subpolar climates, leaving a significant gap when it comes to equatorial and tropical environments, where temperatures are consistently higher, like in Manaus, Brazil. In Latin America, several countries have been establishing goals to reduce carbon emissions and implementing clean energy initiatives. In specifics, Brazil's vehicle markets are also contributing by offering battery-powered vehicles, both hybrid and fully electric models. Inside the state of Amazonas, we can already observe the adoption of EVs and also the use of lithium-ion batteries in solar systems for riverside communities, for example, which provide sustainable energy where access to traditional grids is limited. To better understand how batteries behave under such high temperature conditions, we can use computerized simulations. A powerful tool for that is PyBaMM, the Python battery mathematical modeling library, which allows researchers to simulate battery electrochemical behavior with physical models and submodels in a realistic format. Beyond physical simulations, we can also extract data from PyBaMM and use it to train neural networks. This enables data-driven predictions, such as state of health forecasts, which estimate battery lifespan under various temperature scenarios. So, the goal of this work was to study the effects of Amazonian temperatures on lithium-ion batteries by combining PyBaMM simulations with LSTM-based predictive models. We used real ambient temperature data from Manaus between the year 2022 and 2024 and projected future scenarios for 2032 and 2034. To analyze battery degradation, there are typically three main approaches. First, the physics-based models, such as PyBaMM, as we said, which offer highly accurate electrochemical insights. However, they require high computational resources. Second, data-driven models, such as LSTM neural networks, which are fast and efficient, but their accuracy depends on the quality and amount of data available. Finally, we have hybrid approaches, which combine simulation data with machine learning models. Essentially, the first two topics, while offering a balance between accuracy and computational efficiency. In this work, we adopted this hybrid strategy, using PyBaMM simulation outputs to train an LSTM neural network. Therefore, our methodology is summarized here. First, we customize a DFN model in PyBaMM, the Doyle-Fuller-Newman electrochemical model, and enable several degradation submodels. We also embedded a state of health function, which monitored the variation of nominal capacity on a daily basis, always at the 2 in the morning simulation day mark, and compared it with the specified capacity parameter of the cell. This was made to monitor the degradation capacity over time. The input data consisted of ambient temperature profiles from Manaus, including real data from 2022 to 2024, and projected data for 2032 to 2034. Two projected scenarios were tested. The Type 1 scenario, with an average increase of 4 degrees Celsius throughout the day, and Type 2 with a 4 degrees Celsius increase during the hottest hours, which is from noon to 9 p.m. The current profile simulated a realistic daily cycle, which is 3 discharges at 1.5 amps for 1 hour each, followed by a charging instance of 1.5 amps with a 3-hour duration. We use the Octane 2020 parameter set, which is a LG M50 cylindrical cell. The outputs included capacity and porosity degradation, SEI layer thickness, SOH evolution, and voltage curves. Finally, the LSTM model was trained using the PyBaMM generated SOH data and used to forecast future SOH values for the projected temperature scenarios. Now for the main results. First, regarding capacity degradation. Under Manaus temperature profiles, we observed that lithium plating contributed only for minor losses, while the SEI growth was the main driver of capacity fade. The total loss of capacity at the end of the real temperature scenario was around 0.37 amps per hour. In the projected scenarios with type 1 temperature profile, the hottest one comes reaching 0.40 amps per hour at the end, while type 2, the loss of capacity was at around 0.39. For the anode porosity, it decreased rapidly in the initial months and then stabilized, showing a steady decline over time and accompanying the curve of loss of capacity. Just the same, in the hottest scenario, type 1, the loss of porosity was higher. Specific to the SEI layer, it had a high initial growth rate, stabilizing after about 5 months, and tending towards a slow linear increase in the long term. The state of health function revealed cyclical variations that followed the same behavior as the formation of lithium plating, suggesting a strong relation between it and SEI formation and loss of active material. In this slide, we can see the voltage curves compared between real and projected scenarios. The projected scenarios showed that higher ambient temperatures lead to capacity fade and faster degradation rates. One detail about the simulations is that they get interrupted when the voltage reaches the cell's cutoff value of about 2.5 volts. This, in relation to the month axis, shows that the simulation with type 1 temperatures reaches its end about a month earlier than the other ones. Finally, to present the hybrid approach case, here is a comparison of PyBaMM and the LSTM hybrid model. From the graphs, the results proved there is similarity consistent with PyBaMM SOH forecasts from the same projected scenarios dataset. While not exactly accompanying the same cyclical behavior, the hybrid approach had a much lower computational cost of about 30 minutes compared to PyBaMM's 3-day processing time. With this side-by-side analysis, the hybrid approach showed that machine learning models trained on physics-based data can be a powerful tool for long-term battery degradation prediction. To conclude our study, we've shown that equatorial temperatures significantly accelerate lithium-ion battery degradation, mainly through SEI growth and porosity loss. The hybrid PyBaMM LSTM approach proved effective for analyzing and predicting this process and enabling rapid evaluation of long-term battery health under tropical conditions. This was viable mainly to the fact that there was sufficient data, more than 1,000 days in fact, and taken hourly from the perspective of the PyBaMM's SOH function in the real ambient temperature scenario. In summary, these small insights taken from computer simulations can be considered a trying step towards understanding how batteries behave under such harsh conditions and show perspective to guide the design of firmly resilient batteries, particularly for isolated grids and auxiliary services in hot climates like the Amazon. Thank you very much for your attention.